Okay, so now that we have our steps to performing nodal analysis, let's take a look at a simple example. So this example is going to be good because it's a simple resistive circuit, but it also contains a voltage source and a current source, so we can see how to handle both of those with this method. And we can see from this prompt down here, what we're going to want to do is use our nodal analysis to find the values of our branch currents, which are labeled as A sub I, A sub B, and A sub C. At any point too in these lecture videos, I would encourage you to pause the video and try to work through the problems by yourself. Maybe not necessarily for this one since this is the first time we're using this technique, but just in general throughout the course. Okay, so to solve this simple example, what we're going to do is we're going to step through that 5-step process that we talked about in the previous video. So we're kind of going to combine steps 1 and 2 here with our circuit. And so that's just so I don't have to redraw it too many times. So let's look at steps 1 and 2. Okay, and let's get our circuit down here again. Just paste it to make things a little easier. Get that a little, there we go. Okay, so here's our circuit. So the first thing we want to do is identify where our nodes are. So our node, remember, is anywhere where we have 2 or more elements coming together. So we notice here we have a node, here we have a node, and so really it's all along this area highlighted here. So anywhere where I can travel without having to go through an element, that's going to be a node. The same way over here on this left corner, I could have drawn it as this whole area here. We see we also have another node here, which extends to all of these areas, and then finally this whole bottom area is going to be a node. And so that's because electrically everything in these highlighted, in any given highlighted region, is the same point because we travel through it without traveling through any component. So we could say this top left is a node, whereas the other 3 are going to be essential nodes because the other 3 have 3 or more elements connected. So for instance, in the bottom, we have on the left our 10-volt source connected, our 5 ohm, our 10 ohm resistors connected, and our 2 amp current source connected as well. So we've identified our essential nodes. So we see we have 3, so we can go ahead and write, we know that n sub e equals 3. We don't have to write that, but we'll just kind of keep track of that. So step 1 then also includes identifying a reference node. And so we can do that again by using that arrow notation. So I'm going to choose this bottom node to be my reference node. So I'm going to put my little arrow to indicate that this is going to be our common reference for all of our other nodes. Now the reason that I've chosen the bottom node is because it has the most things connected. It has 4 elements connected as opposed to 3 for our top 2 essential nodes. And as we write our node voltage equations, you'll see why it's preferable to have fewer items connected to the nodes where you write equations. So that's sort of one of those tricks I mentioned about choosing a good reference node. Okay, so now that we've essentially completed step 1 at this point, and the next thing is to label our node voltages. So step 2 is to label our node voltages. And so our node voltages are always going to be negative at the reference node and positive at the node of interest. So let's label this one V1 for instance. So same thing over here with our node in the top right. It's going to be positive at the node of interest and negative at the reference node. And we can call this V2. So what you might see in addition to or instead of that notation, we could also just have a 1 up here by this node indicating that that's node 1, and that would imply that we have V1 between node 1 and the reference as I've drawn. We could also have a 2 over node 2 indicating that that's node 2. So again, you might just see the number above the node, you might see the voltage explicitly labeled, or you might have both. Or sometimes you might have to define this by yourself. Okay, so that's steps 1 and 2. We've identified our essential nodes, chosen our reference node, and labeled our node voltages. The important thing being that our node voltages are always negative at the reference node. Okay, so now on to step 3. So for step 3, remember that we're going to have to write a KCL equation for each of our non-reference essential nodes. So in that case, that means we're going to need a KCL equation for node 1, and for node 2. We do not need to write a KCL equation for our reference nodes. So now what we're going to do is take a closer look at writing each one of those equations. And so remember, we're going to start out using KCL, and then we're going to use Ohm's law and KVL to sort of help us break it down further. So let's just come down here and copy our circuit again, paste our circuit again rather. Okay, so here's our circuit. So what we're doing is we're, of course, like I said, doing KCL, and the convention is that we're going to write all of our currents as leaving the node when we're looking at that node. So all currents leave node of interest. Okay, and so sort of the key thing there is we're talking about our currents are leaving the node. And I'll show you what that looks like here in a little bit. So let me just go ahead and add back in we had our reference node was down here in the bottom. We had this was V1, and we had this was V2. Okay, so now we're looking at node 1, which is this top left, or middle left, we could say, node, or top middle. I'll get it eventually. So what we want to do is, if we're looking at this node here, we are, by convention, defining the currents as leaving this node. So we could, for instance, have I1 going out the left, I2 coming out the bottom, and I3 coming out the right, like that. So now what we're going to do is simply write a KCL equation for this node. So we come down here and we do KCL. And so remember, Kirchhoff's current law is just saying the sum of the currents in, which in this case is 0, is equal to the sum of the currents out. So I1 plus I2 plus I3. All of the currents are leaving. And so of course, physically what that means, we can't have all of the currents leaving the node unless they're all 0. So physically that means at least one of these currents is going to be negative valued. So at least one is actually coming into the node and the others are leaving. Okay, so we've written our KCL equation, but that's not too helpful because we just added 3 more variables and now we have some simple equation. So here's where we want to use our Ohm's law and our KVL to help us get this in terms of node voltages. So in order to do that, we're going to have to define some voltages up here. So I can define a voltage across here as V1 ohm, and of course I'm going to need a polarity, so let me do plus and minus like this. And the reason I've done that is now this I1 is going through a voltage drop, which means that for any equations relating IV, I'm going to need a positive sign. So basically I don't have to introduce a negative sign. So we know that from passive sign convention. Similarly, over here, I can call this voltage V sub 2 ohm, such that I3 is going through a voltage drop V2 ohm. Perfectly fine if you wanted to find voltage polarities opposite. You would just have to insert a negative sign when you do your Ohm's law. Okay, so we've got our voltages and currents defined there. So now let's use not quite there yet, not quite to KVL. We're going to do Ohm's law, and we're going to use that to step towards getting our node voltages into that KCL equation. So let me go ahead and write our I1, I2, I3 on one side, and we'll set it equal to 0 later. So our I1 is just going to be V1 ohm over 1 ohm. Our I2 is just going to be V1 over 5 ohms. And then our I3 is going to be V2 ohms over 2 ohms. And that's equal to 0. So we're almost there because we've got this V1, which is a node voltage, but now we have this V1 ohm and V2 ohm, which are not node voltages. So the next thing we want to do is get each of those in terms of our node voltages. And the way that we can do that is by using KVL. So for example, what we can do is we can do a KVL around this loop to get our V1 ohm in terms of V1 and the 10 volt source. And we can do a KVL around this loop to get our V2 ohm in terms of V1 and V2. And remember, with KVL, we can go any direction, start at any point, but I've just drawn this to make it a little easier to solve for V1 ohm and V2 ohm. So if we start in this top left corner and go clockwise, we have that V1 ohm is equal to V1 minus 10. So we have V1 minus 10 over 1 ohm. And so all I've done is just substituted, because we know V1 ohm is equal to V1 minus 10. Of course, our V1 over 5 was already in terms of a node voltage, so we can leave that as it was. And then our KVL in our middle loop, I'm going to start in this top right corner at the middle loop and go counterclockwise. And what that's going to allow me to do is just say V2 ohm is equal to V1 minus V2. So that's divided by 2 ohms. And so again, that V1 minus V2 is equal to the V2 ohms. So all of that is equal to 0. Okay, so finally, I have an equation that is just our node voltages, in terms of our node voltages and constants. So we would say this is our node 1 equations. Typically what we're going to want to do is simplify, and so there's a couple things that we can do to simplify. So almost always we're going to want to gather our terms. So that means we want to get our V1s together, our V2s together, and so on. Another thing that we can do is we can multiply by our least common denominator, or sorry, least common multiple of the denominator. And so what that's going to do is get rid of the fractions. Personally, I usually don't do that just to avoid making math errors, but I know it is a lot easier to deal with integers as opposed to fractions. So whatever your personal preference is, feel free to do that. In this case, if we take this equation and we multiply it by 10, we can get rid of those fractions, and we have 10 times V1 minus 10 plus 2 times V1 plus 5 times V1 minus V2. All of that is equal to 0. We can then multiply through those terms and collect to get 17 V1 minus 5 V2, which is equal to 100. So we would say this is then our simplified equation for node 1. Okay, so now we've got our node 1 equation. Let's move on to node 2. So let's look at our node 2 equation. And let's just paste our circuit down here again, hopefully make things a little easier on us. Okay, let me add back in our reference node was here in the bottom. We had V1 and V2 defined as such. So now we're looking at node 2 over here. Now again, remember, by convention, we're going to define these currents as leaving the node. So let's say we have I4, I5, and I6 coming out of this node here. So we're going to go through the same process in terms of writing our KCL equation. So from KCL, we have our currents out, our I4 plus I5 plus I6 is equal to the sum of our currents in, which is 0. So now we can use Ohm's law to help us get these currents in terms of voltages, and then the next step we'll do KVL to help us get them in terms of our node voltages. So in order to do that, let's go ahead and define a voltage here. So we can define a voltage V2 ohm primed. And notice now the polarity is such that I4 is going through a voltage drop. So again, when I'm using passive sign convention, I can include a positive sign. So now let's come back here and using our Ohm's law and the knowledge of that current source there, we can simplify this a little bit. So our I4 is going to be our V2 ohm primed divided by 2 ohms. Our I5 from Ohm's law is just going to be V2 over 10 ohms. And then our I6 is just going to be -2 because we have 2 going in the opposite direction of I6. And all of that is equal to 0. And so this kind of proves what we were talking about earlier as far as physically one of these 3 currents is going to have to be negative, at least one, or they're all 0. Okay, so now we've got this, but it'd be really nice if we had it in terms of just our node voltages, so we want to find an expression that relates that to our node voltages V1 and V2. And so of course we can do that with a KVL around this middle loop here. And so doing that Kirchhoff's voltage law, what we find is that the V2 ohm primed, I should say, is equal to V2 minus V1 over 2 ohms. And so again, all I've done is just substituted because V2 ohm primed is equal to V2 minus V1. And then the other terms don't change because they were already either in terms of node voltages or constants. So we have this. So before we move on, one thing to note is that we don't necessarily have to write this out each time. As you get more comfortable, you don't need to write explicitly out the KCL and the Ohm's law steps. You can come straight to this third equation once you get more comfortable. And you can actually go past that to the simplified form if you get really proficient. It's also not necessary to define these currents and voltages at each node. Instead, what we could do is we can use sort of a simplified equation where we say, let's do this in brown, we can say in general the current that we're looking at is going to be the node of interest, so the node of interest minus V at the adjacent node divided by the resistance that is connecting them. So for instance, if we're looking at this current I4, so if we're looking here at I4, we could say, well, our node of interest, our V of interest, would be V2. Oops, let's go back to that. So we'd say it'd be V2. And let me put this a little further down so I don't have to erase it. So that would be I4 is V2. Now our adjacent node would be this one over here. So that's of course V1. And then divided by the resistor connecting them, which is of course our 2 ohms. And so you can see we could have come directly to this form here. Again, as you get more comfortable, you'll be able to do that a little more easily. The other thing that I want to point out, though, is this contradiction where when we were doing node 1 analysis, I had I3. So let me point this out. I had I3. Get a color that's different. So I had I3 going from left to right. Then when we did our node 2 analysis, I had our I4, which was going from right to left. So how does that make sense? How can I have the currents going opposite ways? Well, of course, the current physically is only going one way, and I've just defined these a little bit differently. So if we look a little closer, we can see that we have I3 is equal to negative I4 because they're going in opposite directions. Now, if I substitute in what I solved for I3 in our node 1 analysis, that was equal to V1 minus V2 over 2. And then negative, if I sub in what I had for I4, that was V2 minus V1 over 2. So as expected, these are the same thing. So now let's go back to simplifying this node equation we had for node 2. So in this case, if we want to simplify this and clean this up, we can multiply this by 10 and collect terms. And what that's going to give us, we would have 5 times V2 minus V1 plus V2 minus 20 equals to 0. Collecting terms, we now have negative 5 V1 plus 6 V2 equals 20. So this would be our node 2 equation in simplified form. Okay, so we have our two equations, and we could have known that we needed two equations right off the start because we said n sub b equals 3. So we're going to have 3 minus 1, or n sub b minus 1, which is equal to, of course, just two equations. So now in our fourth step, what we're going to be doing is solving those equations. So step 4 is just solving our two simultaneous equations. So just so we have them both here, we have 17v1 minus 5v2 equals 100, and minus 5v1 plus 6v2 is equal to 20. And so like I mentioned earlier, we can use substitution or linear combination, but these are going to become less practical as our circuits get more complex. So what I want to focus on doing is the matrix method. And so this can be done pretty easily with use of a calculator or MATLAB or Octave or anything like that. But essentially what we're doing is we're saying we have matrix A times matrix X is equal to matrix B. And so what each of these matrices are is this is our coefficient matrix. And so our coefficients are going to be our 17, our -5, our -5, and our +6. Our X here is our variable matrix. So these are our variables. And so of course in this case our variables are our V1 and our V2. And then finally over here this B matrix is just going to be our constants. And so our constant matrix in this case is going to be made up of our 100 and our 20. Okay, so of course what we want to solve for is our variable matrix. So doing some matrix math, what we can do with this general equation is we can say we want to solve for this matrix X. Well, that's going to be equal to matrix A inverted times matrix B. And so again, typically we're going to solve this with a calculator or your computer. You can do it by hand. That's pretty easy for 2x2 matrices, but anything above that, it gets a little tedious. So I recommend you get used to solving this by hand. So in this particular case, if we plug in from our equation up there, we have our variable matrix is V1, V2. Our coefficient matrix, the first row is coming from our first equation, so that's going to be our 17 and our -5. So 17 and -5. Our second row is coming from that second equation, so that's going to be -5 and +6. We're inverting that matrix, and then we're multiplying by 100 and 20 in our constant matrix. And so when we solve that, that's going to give us a matrix as a result, of course, and it's going to give us that V1 is 9.09 repeating, and our V2 is 10.90 repeating. And so the units of that are going to be in volts, because everything in our node voltage equation was in terms of ohms and amps. Okay, so we've solved for our node voltages V1 and V2, but remember back to our problem statement, we actually wanted those branch currents IA, IB, and IC. So let me just paste our circuit one last time here so we can look at what that is. Okay, so we had, one last time, let's define, we had our reference here, we had V1, we had V2 here, and then let me just make sure I get these right here. We had our IA defined here, our IB defined here, and our IC defined there. And so now we're using those node voltages to relate, to figure out what these branch currents IA through IC are. So that's going to be our step 5, and we're just finding values of interest. In this case, it happens to be currents. So for our IA, what we could do is we could say, well, we've already have terms for all of our currents. And remember previously, we had defined an I1 as going here. So what we could say is that this IA is really just negative I1. And so that's equal to negative, and previously if we went up to our analysis, we could see I1 was V1 minus 10 over the 1 ohm. Now we have a value for V1 that we solved for in step 4, 9.09. So plugging that in, we would have negative 9.09 minus 10 divided by 1, which would give us about 0.90 amps. For our IB and IC, it's going to be a little more straightforward. We could relate them to currents we had previously. For instance, our IB was I2 in our analysis up above, or we could just use Ohm's law to say that that is V1 over 5. We plug in the 9.09 and we see that this is 1.81 repeating. Similar thing for our IC. We could say that our IC was our I5 for our node 2 analysis, or from Ohm's law we could just see that that is V2 over 10 ohms. Plugging in our V2, which we found here to be 10.9 in step 4, we would get 10.90 divided by 10 is equal to 1.09 amps. Okay, so I know that example was a little lengthier, but of course that's because I was highlighting every part of every step. As we'll see in some of the examples in future videos, we don't necessarily need to spend that much time writing each equation. But as always, if you do have any questions about any steps or any parts of the process, please don't hesitate to ask me questions.